So in the previous lesson, we studied differential operators. That is where we took a function and then we transformed that function via differentiation into another function. Now in this lesson, we are going to focus on what we call the Laplace transform, which is an integral operator. Now with the Laplace transform, what we are going to do is to select a function of a real variable, which is usually in the time domain, and then we transform this function via integration into another function of a complex variable s. Now this new function is said to be in the s domain or the complex frequency domain. So basically we select a function and then we transform that function from the time domain to the complex frequency domain. So given a function f of t, which is defined for all values of t greater than or equal to 0, the Laplace transform of that function is given by f of s is equal to, we have the improper integral from 0 to infinity of e to the power negative st times f of t dt for all values of s for which the improper integral converges. So two conditions for the Laplace transform to exist. One, we say that the function f of t should be defined for all values of t greater than or equal to 0, or should be defined in the interval close bracket 0, comma, plus infinity, open bracket. And then secondly, the improper integral must also converge. So basically, if you look here, you realize that we plug in a function of t and then we obtain a function of s. So we plug in a function of time and then we obtain a function of s. Now the Laplace transform of the function f of t, which is given as f of s and is equal to the improper integral from 0 to infinity of e to the power negative st times f of t dt, can as well be represented as, we are going to take the limit as m approaches infinity of the integral from 0 to m of e to the power negative st times f of t dt. Now the reason why we want to take the limit as m approaches infinity is that in actual sense you cannot evaluate infinity. What we can only do is to take the limit approaching infinity. That is why we take the limit as m approaches infinity. Now we need to understand that there are some functions that usually occur in nature. We have examples as exponential functions, sine functions, cosine functions, and the like. Now what we are going to do here is to select at least one or two of these functions that usually occur in nature, and then we try to derive their Laplace transforms. So the first function we are going to start off with is the function that is the exponential function f of t, and that is equal to e to the power at. So let's start off with this exponential function. So we can as well represent the Laplace transform of a function as we have L, and then we have the Laplace bracket of the function, and then we have e to the power at. So this is equal to, we have the improper integral from 0 to infinity of e to the power negative st times f of t dt, and this is equal to, we have the limit as m approaches infinity of the integral from 0 to m, and then we have e to the power negative st times f of t, which is e to the power at dt. Now let's try to solve this. So we have the limit as m approaches infinity of, we have the integral from 0 to m, and then let's try to simplify this. So we have the bases to be the same, so we have e to the power, now we have negative or minus on the outside, so negative 1 times s is negative s, so we have negative 1 times s, and then negative 1 times negative a gives a, so that becomes minus a, and then all times t dt. Now the next thing we are going to do, we take the limit as m approaches infinity, and then we try to integrate this function. So we are going to have, now to integrate this, we can take this as having the integral of e to the power negative 2t dt. To integrate this, what we are going to do is, you are going to first of all rewrite what you have here, that is e to the power negative 2t, and then you differentiate the exponent with respect to t. So derivative of negative 2t with respect to t is negative 2, and that negative 2 appears at the denominator. So that is exactly how we are going to treat this. So first of all, we have e to the power negative bracket open s minus a bracket closes t divided by, now because we are going to integrate with respect to t, negative into bracket s minus a becomes a constant. So when you integrate the exponent, you have negative s minus a, that is from 0 to m. Now let's continue. So this becomes, we have the limit as m approaches infinity of, we simplify this, or we try to represent it in a more nice way. So negative 1 over s minus a times, now we are going to evaluate the upper limit minus the lower limit. So we have e to the power negative into bracket s minus a, and then in place of t we have m minus e to the power negative into bracket s minus a. In place of t we have 0. Now in the next step, we are going to do two assumptions. So first of all, we are going to assume that s is greater than 0 and then m approaches infinity. So these are the two assumptions we are going to make, and then we are going to have negative 1 over s minus a. So the limit goes away, and then we have this fraction multiplying. Now as m approaches infinity and then s greater than 0, we have what's in the bracket to be a positive value, and then times infinity, which is also positive, and then times negative, which is negative infinity. Now e to the power a value which is very close to negative infinity is equal to 0 minus, here because we have 0 here, so the exponent becomes 0, and then e to the power 0 is equal to 1. Now let's try to multiply the two values. So we have negative, it becomes positive, and then we have 1 over s minus a, where s is greater than a. Therefore, the Laplace transform of the function e to the power at is equal to 1 over s minus a, where s is greater than a. So this is the Laplace transform of the exponential function e to the power at, and this is how to derive that. Now let's look at the second function. Now the second function, we are going to consider the function f of t equals to 1. Now f of t equals 1 is a special case of e to the power at, where a is equal to 0. Now if a is equal to 0, we have the exponent to be 0, and then e to the power 0 is equal to 1. So the function f of t equals 1 is a special case of e to the power at, that is where a is equal to 0. Now to find the Laplace transform of this function, basically we are going to use the transform we had in the previous function. So we had the Laplace transform of the function e to the power at to be equal to 1 over s minus a, where s is greater than a. Now since we have in this case a to be equal to 0, then basically we say that the Laplace transform of 1 is equal to, we have 1 over s minus a is equal to 0, so 0, and that is equal to 1 over s, where s is greater than 0. So now we have been able to derive the Laplace transforms of two functions, that is first f of t equals e to the power at, and then f of t equals 1. Now aside from these two functions, there are some more functions which also occur frequently in nature. We are not going to derive such functions. What we are going to do is to construct a table where we have all these functions in there, and then we try to take examples of each form of the function, and that is going to help us to obtain the Laplace transform of certain other complex functions. So for now, we know two functions with their respective Laplace transforms. So to fill our table, we are going to consider the first function, which is the function f of t equals 1. So we have the Laplace transform of 1, and then we already know that this is equal to 1 over s, where s is greater than 0. So let's try to find the Laplace transform of, let's say, the function f of x equals 2. So how do we find the Laplace transform of this function? Now, before we can solve this problem, we need to know the property of Laplace transform, which we call the linearity property. So this is the linearity property. Now this property states that assuming we have two functions f1 and then f2 with two constants c1 and c2, so that we have the Laplace transform of the function c1 f1 plus c2 f2, then we can split these two so that we have the Laplace transform of c1 f1 plus the Laplace transform of c2 f2. Now, because c1 and c2 are constants, we can pull them out so that we have c1 the Laplace transform of f1 plus c2 the Laplace transform of f2. So basically, that is what we are going to use here. So we can represent this as the Laplace transform of 2 times 1. And then because 2 is a constant, we pull out 2. So we have 2 times the Laplace transform of 1. And then we already know the Laplace transform of 1 as 1 over s. So we have 1 over s here. We multiply 2 across so that we have 2 over s, where s is greater than 0. So the Laplace transform of 2 is equal to 2 over s. Now let's move on to the second function. That is the function f of t equals e to the power at. So that is, we have the Laplace transform of the function e to the power at, and that we know is equal to 1 over s minus a, where s is greater than a. So assuming we want to find the Laplace transform of the function, let's say 3 e to the power 5t. So using the property of linearity of the Laplace transform, we can pull out 3, which is a constant, and then we have the Laplace transform of the function e to the power 5t. So comparing these two in the Laplace bracket, you realize that we have a to be equal to 5. So using this transform, we have 1 over s minus 5, and then finally we have 3 over s minus 5, where s is greater than 5. Now let's move on to the third function. We are going to consider the function t to the power n, where n is equal to 1, 2, 3, and so on and so forth. Now the Laplace transform of this function is said to be equal to n factorial divided by s to the power n plus 1. So for example, if we consider the function t cube, we want to find the Laplace transform of this function, then we know that n is equal to 3. So we have 3 factorial divided by s to the power 3 plus 1. Now 3 factorial is 3 times 2 times 1 divided by s to the power 4. So finally we have this to be equal to 6 divided by s to the power 4. Now let's move on to the fourth function. So for the fourth function, we have the function f of t. We have f of t equals e to the power at times t to the power n. Now this is said to be equal to the Laplace transform of this function is said to be equal to n factorial over s minus a exponent n plus 1. So this is quite similar to the third function. The third function is t to the power n, and then this function is e to the power at times t to the power n. So taking an example, let's say we want to find the Laplace transform of e to the power 3t times t to the power 2. So this will be equal to, we are going to have n factorial. Now t to the power 2 and then t to the power n. Comparing these two functions, you realize that n is equal to 2. So we have 2 factorial divided by, we have s minus a. A is 3, and then to the power n, which is 2, so 2 plus 1, and then we have this to be equal to 2 factorial is 2 times 1, which is 2, divided by s minus 3 exponent 3. Now let's move on to the fifth function. Now the fifth function we would like to talk about is the function f of t equals sine at. Sine at. So the Laplace transform of this function is said to be equal to, we have a divided by s square plus a square. A divided by s square plus a square. Now we are going to take an example. So we want to find the Laplace transform of the function sine 2t. Sine 2t, and this is equal to, now the value of a here is 2, so we have 2 divided by s square plus a is 2, so 2 square, and this is equal to 2 divided by s square plus 4. Now to the sixth function, we want to find the Laplace transform of the function cos at, that is also given by s divided by s square plus a square. So taking an example, we want to consider the function cos 2t. So we want to find the Laplace transform of this function. This is also equal to, we have s divided by s square plus a square. Now we have a to be 2, so 2 square. This is equal to s divided by s square plus 4. So note the difference here. If you have the Laplace transform of sine at, that is a over s square plus a square. If you have the Laplace transform of cos at, that is s over s square plus a square. So for sine you have a, for cos you have s. Now let's move on to the seventh function. So the seventh function we are going to consider here, we are going to consider the function f of t equals sine of at, and that is equal to a divided by s square minus a square, where s is greater than a. So taking an example, if you want to find the Laplace transform of the function sine 4t, then that is equal to, we have a to be 4, so 4 divided by s square minus a square, so 4 square, and that will be equal to, we have 4 divided by s square minus 16. Again, we move on to the eighth function. We have the Laplace transform of the function cos at, that is also given by s over s square minus a square. So we take an example, that is, we have the Laplace transform of the function cos 4t, that will be equal to s divided by s square minus a is 4, so 4 square. That will also be equal to s over s square minus 16. Also notice the difference here. Now to the 9th function, we are going to consider the Laplace transform of the function t sine at, t sine at, and that is equal to 2as divided by s square plus a square all square, s square plus a square all square. So taking an example, we are going to consider the Laplace transform of the function t sine 2t, t sine 2t. Now this is equal to, we have 2 times a is 2 times s divided by the denominator we have s square plus a, which is 2, so 2 square all square. This is equal to, we have 4s over s square plus 4 all square. So this is the Laplace transform of t sine 2t, t sine 2t. Now let's move on to the 10th function we are going to consider here. That is, we have the Laplace transform of the function t cos at, t cos at. Now this is given as s square minus a square divided by s square plus a square all square. We also consider an example, that is the Laplace transform of t cos 2t. This is also equal to, we have s square minus, now a here is 2, so 2 square divided by s square plus a is 2, 2 square all square. This is equal to s square minus 4 and then divided by s square plus 4 all square. To the 11th function, we consider the Laplace transform of the function sine at plus b, sine at plus b. This is nothing but s sine b plus a cos b, all divided by s square plus a square. So we take the example, the Laplace transform of sine 3t plus 5. We say this is equal to, we have s and then sine b, b here is 5, so sine 5 plus a, which is 3, cos b, which is 5, all divided by s square plus a square, so 3 square. Now 3 square is equal to 9, so we simply write 9 here. To the 12th function, we have the Laplace transform of this time cos at plus b. We say this is equal to, so with the cos, we are basically going to interchange the positions of sine and the cos, and then we negate this operation, so this becomes negative. Instead of addition, it becomes negative. So here we are going to have s cos b minus a sine b, all divided by, the denominator remains the same, so s square plus a square. So for example, if we consider the Laplace transform of cos 3t plus 5, then here we have s cos b, and then b is 5, minus a, we have a to be 3, so minus 3 sine 5, all divided by s square plus a 3 square. Now 3 square is 9, so s square plus 9. Now we move on to the last two functions. So we have the 13th function, that is f of t equals e to the power at times sine bt. So we want to find the Laplace transform, or we want to write down the Laplace transform of this function. Now this is given by b divided by s minus a all square plus b square, where s is greater than a. So for example, we want to find the Laplace transform of the function e to the power 4t sine 5t. So we have b to be 5, so we have 5 on top, and then we have s minus a is 4, so s minus 4 all square plus b we know is 5, so plus 5 square. Now this is equal to, we are going to have 5 divided by, now let's expand this. So s times s, we have s square, s times negative 4 is negative 4s, negative 4 times s is also negative 4s, so negative 4 minus 4 is negative 8, so minus 8s, and then negative 4 times negative 4 becomes plus 16, and then plus 25. So finally we have this to be equal to 5 divided by s square minus 8s, and then plus 41. Now to the 14th function, we are going to take the Laplace transform of e to the power at, this time cos bt, and the transform is given by s minus a divided by s minus a all square plus b square, where s is greater than a. Also considering the example, the Laplace transform of e to the power 4t cos 5t, so we are going to have s minus a is 4, so s minus 4 divided by s minus 4 all square plus b square. So this is equal to, we are going to have s minus 4 divided by, so the expansion for s minus 4 all square gave s square minus 8s plus 16. So here we have s square minus 8s plus 16, and then here we have b to be 5, so 5 square is 25, and this is equal to s minus 4 divided by s square minus 8s plus 41. So that's it for today's video. Now in the next lesson, we are going to consider the elementary properties of Laplace transform.